Hello, people. How's it going? I'm assuming things are going okay. So, one of the things that we're at here is that I want to sort of like briefly review of what we did last time. And one of the things is that I want to share a couple of things with you first. So, the first thing that I want to do here is that I want to go into my screen to just sort of like remind you of one thing. And it's a very simple equation that I wrote, but I want to look at something like this here. So what we said last time here is that when I look at the special theory of relativity, what we're doing here is that we're doing something like this here. I said that Einstein and the principle of special relativity said that all the laws of physics are invariant for all inertial observers. So from Maxwell's equations, we saw here that the speed of light was always equal to a constant. And one of the things that I was saying here is that if the speed of light is a constant, since speed is not very complicated, I said that this distance over time should be the same no matter what. And what I tried to say in this language here is that I said this, that space-time must adjust itself to keep c equal to a constant. And what I said here is that this is a very disturbing thing, because our Newtonian common sense says no way. And the example that I said is that if you lived in Santa Cruz and somebody asked you, how long does it take to go, drive to San Francisco? We're all going to say that the distance is, roughly 75 miles. But Einstein, with the principle of relativity, says that that's not true. And I'll try to explain that a little bit later, but the bottom line is he says that it's not true. And so what this statement is telling me here is that different observers measure different distances and different time intervals, right? That's what this is telling me. Different observers measure different space and time intervals. And so the statement that I like to say here, it's in the eye of the beholder. And what's shocking about this statement here is that if two observers measure different quantities, then that measurement or that quantity has no objective reality. And I think that's what's really hard. I mean, think about that. We think about distance and going like, wow, yeah, the distance from here to San Francisco is 75 miles. But if we talk to somebody else that's moving at some fast enough speed, they're going to say, it's not 75 miles. What are you talking about? So distance has no objective reality, which is shocking. So what we want to do here is that the way we visualize this, and the easiest way to visualize this thing, is that we talked about the light clock. And the light clock is really about different observers measuring different times. Okay, and so what I have here is that I have a light clock applet, and I want to show you what I have here. So if I go in here and I'm going to do a new share for this light clock, here's this light clock. And so this light clock here has Jack and Jill here. And so if I run this, which it runs very slowly, you could see that there's a beam of light from the source. It goes up to the top, it reflects, and it comes back down. So it's measuring, that's the path. So if you look over here to the right, note that Jack's clock reads 8 seconds, Jill's clock reads 8 seconds. Because there's no relative motion between Jack and Jill in this app, then they measure the same time distances and they measure the same distances. But now what I'm going to do here is that I'm going to come over here and I'm going to change the speed of one of the clocks. So now when I run it, Jill is going to be moving relative to Jack. And so now what you're seeing here is that if we go to tick, you could see that Jack's already tick, Jill is later. So by the time it gets back, you could see that these two guys measure two different times of the tick and the tock here. So if I look at Jack's clock, because he's measuring relative to his frame, he measures 9.78 seconds. But when you look at Jill's clock, because of the motion, it takes longer for the beam of light to actually kind of reflect off the mirror. And so it takes longer to go from tick and tock. And it's this time change. And essentially, that's what Einstein had to deal with the very beginning. Once he understood the time issue, then he said he understood everything, and then he wrote special relativity very, very, very quickly here. So what I want to do here is I want to talk about just a couple of remarks before we move on here. And the first remark here is that when we said, so when we talk about special relativity, it literally means V is equal to a constant, or in other words, zero acceleration. If acceleration is not zero, that means you're in a non-inertial, let me go back, a non-inertial frame of reference, then you need the general theory of relativity. Now, there's a huge jump between special relativity and general relativity. This allows us to calculate situations of acceleration. And another thing that I've said here a couple of times now, special relativity is battle tested. And what I said here, it has been verified more than Newton's laws. And that sounds kind of crazy, but it's true. Very few people in this world believe that special relativity will never be overthrown. So that means if I'm in situations of constant velocity, nobody that I've ever met believes special relativity will ever be, you know, come up with a different theory. Now, what the general theory of relativity does is that it includes special relativity and situations of non-inertial frames of reference. You can expand on special relativity by general relativity, and you'll see that a lot of times people call it just GR, but it's definitely not wrong. And the other thing here, I mean, I said this, several times already. It really did take a genius like Einstein to come up with the relativity. And the reason why is because when you look at speed and we think about distance and time, I mean, these are the most basic, right? Basic ideas in all of science. You cannot talk about anything without talking about distance. And time is really a distance measurement. And I actually don't want to get into that too much here. But to give you a sense of just how radical this thing is, there's a pretty good analogy that I've sort of like have depended upon, over the years here. And Einstein really did mess around with the foundations in a dramatic way of physics. So he really changed the foundation of physics in a very dramatic way. And the analogy that I will just show you how radical this is, imagine that you have a door that is sort of like rubbing against the frame.
I can't wait for this one.
Okay, so you could imagine, so if you have a door, let's say that here's the frame, right? So there's the frame. And then the door is a little bit off. So what you do here is that you could imagine that the door is sort of like, maybe it's rubbing right there, and it comes back down and it does something like this. So what you're seeing here is that here's where the rubbing is occurring. Now, most people are going to do what? They're going to take a planer, hopefully an electric planer, and literally just plane the top of the door so that it's now lower than the door frame, so that then it could just do that, right? That would be the so-called normal thing, is to plane the top of door. So what did Einstein do? What Einstein did, he did something radical. So now you could imagine that you have the house. And now you have this door frame here. And what he essentially does here is he comes in here and he puts a jack underneath the house. And what does he do? He starts taking this he puts in his little tire iron, if you want to say, and he starts jacking up the house. So what happens? He takes this whole door frame, and what does he do? he now tilts it at an angle. So when you now go look at the door doesn't rub anymore. He literally takes the foundation of the house, kicks it up a little bit, and radically changes this house here. Essentially, this is what Einstein did to physics. He really radically changed the viewpoint, right? If you were to do this, I would call you stupid. But he did this to physics effectively. So it's not some small little tinkering. He really changed it. And then, he radically changed what we now know as the photon, and his general theory of relativity is another of these foundational changes in what actually happens. But ultimately, that's what's actually happening right there. So what we want to do here is that we want to keep moving now. Okay? We want to keep moving, and we want to get into the consequences of Einstein's principle of relativity here. So what we do here is that now that we understand the principle of relativity, we now want to go in and we want to look at the consequences of the principle of special relativity. That's what we want to do. We want to go look at the consequences. And what we said here is that it took Einstein a little bit of time to do that, but once he got the right idea, he derives the Lorentz boost. And remember what the Lorentz boost does. It tells us that we could boost from one frame into another frame. And when you look at this thing here, when you do this, what you're getting in this Lorentz booster is that you're getting a mixing of space and time. And if you're getting a mixing of space and time, we now call it space-time. Now remember, that's a crazy statement, because that's not the way we view the world here. And what we said here is that if I look at the Galilean, transformations, you can also call them Galilean boost, by the way, but it's more common to call them Galilean transformation. And what we said before here is that we can get something like this, or we could get something like this here. And what you're seeing here is that in Galilean, time does not mix with space. Excuse me. So if it doesn't mix with space, then what's telling me here is that special relativity is quite different, because why? We get the mixing of space and time. That's why they call it space-time. And what we said here is that when I now look at the Lorentz boosts here, what we get here is that we get the mixing of these two. And what we wrote last time looks something like this here, where, again, you could see mixing of space and time here, just like you could see with the Galilean transformations. But now, if you look at the time, it's now quite different, because you can see that there's this space, there's this mixing. right? You could see that you're getting position and time mixing together here. And so for right now, I'm only going to focus on this guy here. So what I'm really looking in this picture here is that I have one frame. What do I call that frame? I call that the S frame. And what do I mean by the S frame? I mean a frame that allows me to do what? That if I look at this S frame, for the sake of simplicity, we're going to say that S is at rest relative to the Earth. If I have a prime frame, I have a frame in such a way that it's doing what? It's moving relative to the Earth. So now I can boost from these Earth frame, if you want to say, to this S prime frame moving relative to Earth. And then this factor, we have this gamma factor. So the gamma factor, also known as the relativistic factor. By the way, most people don't call it a relativistic factor, they just call it gamma. And when you look at this gamma factor, you'll see that we ended up writing this thing. And when you derive these new boosts, you're setting conditions here. This gamma factor comes out. But you'll see that I prefer to write it with the beta factor with beta equal to V over C. So this is a huge thing right here. And the way you get these Lorentz boosts here is that you literally are really setting two conditions. One condition is that the speed of light has to be the same for all frames of reference. And the other thing here is that in the limit of V being much, much smaller than C, you should get back the Galilean transformations, which you do here. So now what I want to do here is that I want to just look at briefly at this Galilean, this gamma factor here, and this is what you see here. What you find here is that I have an image that I want to share with you. And let me expand on this thing here. So what I plotted here is that you have a plot of gamma on the vertical axis and beta. So beta just tells you what? Beta tells you about the percentage. So beta is the percentage of C. So that means if I'm traveling at 0.2 beta, then that means you're traveling at 20% of C. And so what you're seeing here is that when you look at this curve, you're seeing that, okay, this window keeps popping up, sorry, is that you're seeing that for a long time here. What's a long time? Up to, you could see that right here, that looks like more than 0.3 or 30% the speed of light. But note that 30% the speed of light is pretty damn fast. I mean, if you were to look at 30% the speed of light, you're finding here that that 30% the speed of light is something like, I don't know, it's probably about 250 million miles per hour, which is crazy, of course. So if you're going 30%, of C, if you, my numbers would probably guess that this is going to be somewhere around 200 to 250 times 10 to the 6 miles per hour. So you're not going some slow speed, you're going something pretty damn fast. So you have to go that fast to start to see something that gamma is not something different than 1. So if I was to step back here, if V is equal to 0, then you could see that gamma is going to be 1 minus 0 over c squared, which will be 1. So gamma factor is 1 at relatively really small values. If you were to pick, by the way, 65 miles an hour, this gamma factor, if you plug this in, you're going to get a value of 10 times 10 to the negative 8. So at everyday speeds of driving highway speeds, assuming you're an upstanding citizen driving 65 miles an hour, this gamma factor is so small that all of the Lorentz boost immediately reduced to the Galilean transformation. So let me show you what I mean by this thing here. So if I just scoot up here, so if one moves, a speed of 65 miles an hour, then your gamma factor is of the order of 10 to the negative 8. So if I now go and I look at the Galilean transformations, what you're going to see here is that if I look at x prime, I'm sorry, what I said was not correct. Let me go back and change to be a little bit more clear, because what I said here is going to be 1.0000001. Okay, that's what I mean by this 10 to the negative 8 right here. So if you're looking at that 10 to the negative 8, I'm really talking about that's where the 1 appears. And I was not clear up here. So if you do that, then I'm going to get what? Gamma times V minus, not gamma. It's got to be X minus VT. And then if I look at T prime, I'm going to have gamma of T minus Bx over C. And what you're going to find here is that this guy, to a very good approximation, is going to be 1 times X minus Vt, which immediately gives you the Galilean transformation. Now, when I look at this guy here, you're going to get 1 times T, and then I'm going to get gamma, or I'm going to get 1 times the quantity Vx over C squared. But V over C is so much smaller than 1 that this thing essentially is just dropped out of the equation. So then this tells me here that T prime is equal to T. So I get back the Galilean transformations at low speeds here. But when you start to look at this gamma factor at higher and higher speeds, you can see that it really starts to take off when you get to, something above, 60% the speed of light. And so the gamma factor, if we start to sort of like look at these guys here, and I'm going to erase these afterwards, look at that. So all of a sudden, if I get to 60% the speed of light, gamma goes from 1 to 1.25. Now that 0.25 doesn't seem like a lot, but look at what it was for, 65 miles an hour. If you go to 85, look how it jumped. It's almost at 1.9. And as you get above 90, then it really starts to take off here. And so that gamma factor is really important when you get to these higher values here. So now that I've talked a little bit about the gamma factor, I want to go into the Lorentz transformations. And the two things that we want to talk about with the Lorentz transformations is that we want to go in and we want to start isolating them. Okay? So two of the consequences, so two consequences of SR is one, time dilation, and two, length contraction.
Hey, Carlos, sorry to interrupt, but if you wouldn't mind scrolling up just a touch, please, so I could copy the last line. Thank
Right
you.
here?
Yeah, it's perfect.
I think you also meant, Carlos, T prime is equal to T.
Yes, I did. So I would take that off right there. Okay. So that's a slip right there. So now, here we go. So let's look at these Lorentz transformations.
Also, your terrible audio quality. I don't know what happened, but
Is
if you
it?
changed anything, I'd change it back.
I didn't change anything actually.
Yeah. Are you on a headset or is you talking directly to the tablet? It's really choppy.
Yeah, it's kind of hard to understand.
I think it's just internet drops because it just gets all robotic. So
Here, I'm trying to get rid of any files that I have open.
And
You
I'm
know what
down
I'm
with
gonna
auto
do?
tune Carlos, but this is
Yeah. Here, how about it?
yeah,
I'm gonna
closing
stop
the
my
extra window should
video.
help.
I'm gonna stop my video just in case it's sort
That
of
will
like
definitely
a
help.
bandwidth issue. Okay.
That should help.
So hopefully that improves it a little bit.
Yeah, that sounds better.
So but it could be that I'm not writing. So that could be it.
Oh, let's
So
try that, huh?
Okay. So one of the things that we want to do here is that let's go back. I'm going to scan back up and I'm going to grab what I wrote right here. And so I'm going to come back here. What I want to do here is just want to focus on moving between these two scenarios here. Okay. And what I'll do here is that by doing this, what I'm actually really trying to show you here is that what really happens here is that this is only one point. Okay, these equations, these are only at one point. But one point is meaningless. The only way we can talk about things is we need to talk about differences in position, what we call displacement, and differences in time. So what I'm going to do here is I want to go in and I want to really start looking at this in terms of differences. So I need to look at differences in space and time. Really differences in space-time. And the books do something really slippery, but don't ever really tell you why they do it. And I want to make sure that I try to explain this thing. So if I want differences in position, then what I really mean here is that I'm saying, okay, here's my delta x prime. And what I mean by this is that I'm looking at the difference between these two. And so what happens, so when I look at the Lorentz transformation, this is the gamma of delta x minus v delta t. So the really important equation is this guy right here. And if I do the same thing with the time, then of course I'm looking at the differences of the time here. And then this guy here is then going to be gamma, the differences in time, that looks something like this here. So the important is this here. Okay, how's that? Is that a little bit better? So now what I want to do here is that this is what we really mean when we're talking about making measurements. We have to make these two measurements. So now what I want to do here is that now they do something silly here. So what you're seeing with these Lorentz boost here, this is really what the Lorentz boost from S to S prime. But what they do here is that they say, okay, now let's look at, since we said we were going to start looking at time dilation, so let's look at time dilation. So if I talk about time dilation, what I'm doing here is I'm really doing this thing. This is what the textbook says here, but man, it has no basis in reality. They say this, if I look at this time, what I'm really writing is I'm writing a relationship that looks like this. And then they come in and they write, okay, then I got b c squared delta x. Now, what do I really mean by this picture here? Well, you could imagine that I have an observer in the S frame. What do I mean by this S frame? This guy is stationary, let's say relative to Earth. Now I have a second situation where I have a space shuttle or something that's going up here, right? So the space shuttle's taking off here. And now I have my second observer right here. So when I look at this frame, this is the S prime frame. And then in this right here, you're moving off with some relative velocity v relative to the Earth. So it's really, really common in this situation. We're going to simplify things. So they're going to say, we are going to simplify things. And what I mean by simplify things is that I'm going to come in here and I'm going to look at this time dilation equation and I'm going to say that, yes, I know that they're moving. Okay? I know that they're moving, but what I'm going to assume here is that delta x is 0. But delta x means that they're doing what? That they're at the same location. So the only way that they could be at the exact location is that these two have to be right on top of each other, which of course is crazy, right? If you had a spaceship that was intersecting you, what's going to happen? You're going to get crushed by the goddamn ship. So physically, it's not possible. But what they really are trying to say here is that you come really close. This is 0. So if this is the Lorentz transformation, then if I can ignore delta x, then this guy is the time dilation equation. Okay? So remember, when they say time dilation equation, you got to remember there's a subtlety here about that position. And if this spaceship, by the way, was some distance x, you could not write just the time dilation equation. That would be wrong. But you're going to see, even though it's wrong, I'm going to be using it considerably in this chapter, even though I know it's wrong. And all we're trying to do is simplify this thing. In order to get the true answer to the time dilation, you have to come in here and you gotta do what? You gotta add that distance. That distance, because space-time is mixed up, contributes to the time dilation. But like I said, 99.9% of all textbooks ignore the delta X contribution. So almost all the dilations that they calculate are technically wrong because they're not including that delta X. And so when we write this equation, just to summarize this thing, so when we write delta T prime, this implies here that this is a very specialized case. Okay? It's a very specialized case. As long as you're aware of that, then we're probably good and we can move on here. So now, I'm going to pull a real fast one here. I'm going to go back to relativity. What does the principle of relativity state? What does it state? Okay. What it states here is that one cannot tell the difference between at rest or moving the constant velocity. So when I look at this time dilation equation here, so if I have a time dilation equation, we just said here is that this was at rest relative to Earth, and this was moving relative to Earth. So in our picture here, what we already said here is that we imagine that we have this observer on Earth in the S-frame, and then we had our rocket or spaceship moving with speed v like this. So in his viewpoint, what he's seen here is that he's seen that there's motion of the rocket relative to that. But according to relativity, you can't make a measurement that can tell the difference between the two. So now look what I'm going to do. I could then perform a boost from S prime to S. And you're not going to like this, okay? If I'm in the frame of the rocket, then I can write this relationship just the opposite. So from the rocket viewpoint, what happens? The rocket is not moving, it's stationary. But what's happening to the observer here in the S frame? This observer is moving with a relative velocity of v. So according to the time dilation equation of the, in this S prime frame, there's nothing special about the S frame or the S prime frame. So look at this time dilation equation. Guess how I'm going to write it? I'm going to write it as what? Delta T gamma delta T prime. Where this is what? This is the moving frame. Oops, sorry about that. this is at rest relative to rocket. And then in this frame, this is moving relative to rocket. No one can say that their frame is a better frame. That's the principle of relativity. So now you could see that this little prime thing of being at rest or moving is all relative to what you're measuring from. Okay? So this is what makes relativity so tricky here. Okay? How's my audio coming along?
It seems like when you stop writing, it becomes fine. Otherwise, it's really been awful.
Yeah, it's been pretty hard to understand the past couple minutes.
Yeah, very choppy,
So let me
unfortunately.
tell you something here. I'm getting on Zoom, it says that your speaker is not working. Please check your connection or use a different speaker. So,
Yeah, you're probably having some sort of connection issue then.
so is that a connection? Because this I'm doing this wirelessly. So my question is, so headset might be the right thing to do?
A headset? I don't.
Or
I
maybe
not.
like just a microphone. You could just get an Amazon.
Just use a
Microphone,
microphone that's separate from. So how would I
Yeah, so then
use
you can
my,
just
is that
you can
useful?
buy one.
here?
They have them at like Best Buy and Amazon and stuff, and you just plug them in through USB. So you just plug them in like a mouse would, and then you just it usually selects it by default, but you can manually just set it so that it always uses that microphone.
So why would that solve the problem?
It seems like he's having some sort of speaker issues as well. He might be having, there might be something wrong with the built-in microphone, my guess, because it doesn't seem like it's internet because he's going in and out, and it is roboting like that. But I don't know, something about it just doesn't seem as much internet because we haven't had this problem as bad in the past, and it's when he's using it, and he's saying he has a speaker error. But honestly, I don't know. It could just do nothing.
When I was with
I'll get a
Car-
microphone and see if I can make that work.
I
I'll
think
get
it's
it
an
by-
Carlos.
Emmanuel?
I think it's an internet connectivity because when we were talking the other day, I was lagging out with you too. Remember that it was yesterday or
Oh, did it happen with you too, Manuel?
yeah, it was in the morning. And
Oh, then it's probably then it's probably just internet.
You know, the one thing that I worry about it is that we just went from 400 megs to 1 gig.
Well, that would do
And
it.
when I checked this, the speed on this tablet, it was almost 400 megs just by itself.
Up or down?
Mhm.
Up.
Oh, God, that's enormous.
Do you?
No,
That's- yeah.
not up. That's down. That's down. Sorry about that.
Okay,
I
what
think
about up?
That could be it.
I don't know what it is actually.
Well, that's what you're doing. You're
No,
sending
I agree.
data
I
to
agree.
their server.
I agree.
Are you on Ethernet or are you wireless?
I'm wireless.
Ethernet might potentially
Surfaces
help
are
if
hard to
down
put
if
on.
up is bad.
Okay, how about if we move on? Maybe we could have a discussion about this some other time, but I think we should just move on right here. So this is a really big challenge right here. And the reason why this is a challenge is that, see how arbitrary I could move that prime around? And this is what makes it really hard. So we need some language. And the language goes something like this. So we define a proper frame. And a proper frame means this, that the observer is at rest relative to the light clock.
See, now it's been flawless.
So you can hear me perfectly fine.
it's the last 30 seconds, 45 seconds, maybe minute has just been completely flawless.
Yeah.
Okay.
Yeah. it's
Even
good.
with you writing, and that was the point that I was making.
And you know what? My Surface had the fan running on. Now it stopped.
I
So
noticed there's a circling arrow thing sometimes in the top rightish corner. What is that? Is it backing up? Is it doing some, is it trying to walk and chew gum at the same time?
no, dude, I stopped all processes.
Okay.
So I don't know what it is.
So I
So
know.
you have to define the proper frame where the observer is at rest relative to the light clock. So what you want to think about this, so when I write down time dilation, I typically write like this, and then this is what I say is the proper time. And if that's the proper time, I have to be careful what the wording of the thing is. And then this here is the time dilated, the time dilated by motion. And remember what I mean by time dilated by motion. It's the light clock. So when I look at this picture here, and I'm seeing this beam go up and down, and I have my little observer right here, he is at rest relative to that light clock. So this observer does what? Well, when he compares the time to the clock that's moving, that beam, like I showed you earlier, takes longer to go from here to here. So this observer in green is the one that has a velocity going in this direction. So this is the proper time. And this clock appears to run faster. Okay, let me be careful. And I'll explain what do I mean by appears, because that's where the word gets tricky here. This is the time dilation. And this clock, we say this clock, again, look what I said, appears to run slower. Now, be really, really careful, because remember what I said. This person measures the time delta t. This person measures the time, let's say delta t prime. These guys will never, ever measure the same values. Because these time differences are different, time has no objective reality. So what we say here, when I say the word appear, relative to the S frame guy, right? This is my S frame. Everything that works here is perfect. But this guy in the rocket here, his light clock is at rest relative to him. So to him, all of his times run perfectly fine. The only time you see a problem with the timing here is when these two observers come together and compare clocks. So the only time that these observers notice a time difference between their clocks is when they come together and compare. Okay? They come together and compare. So what your job is to pay attention, where is the proper time for this question, this problem, this quiz or exam problem, okay? Where is the proper time? One more time, time differences are meaningless. It doesn't make any sense. So if I say that I'm 58 years old in special relativity, that is a meaningless statement. Okay, that's time dilation. Now let's go to length contraction. Okay, so now I'm going to focus on length contraction, and then we'll start trying to put together an example here. Length contraction. You know, another thing that I did with my Surface here is I unplugged it just in case the outlet was interacting with it.
Can you plug it back in?
Sure. The fan is not going off though.
Carlos, I need to copy the line right above real quick. That's cool.
Okay. No problem. So length contraction works exactly like time dilation. What do? We start with Lorentz boost. So what do I know about Lorentz boost? Is that we do this here. We go from S to S prime. Oops. So if I go from S to S prime, if we write down what we did before, we said that I'm essentially looking at something like this. I had X prime is then going to be gamma X minus VT. And so if I look at just the distance here, then if I look at differences in X prime, then I'm going to get gamma delta X minus V delta T. And if I look at S prime over S, then I get the opposite, which I'm going to get X equal gamma X plus VT. So if I look at the differences here, but by the way, yeah, if I look at the differences of this guy, I'm going to get delta X equal to gamma delta X prime plus V delta T prime. So in a very analogous way here, they'll say, let's focus, right? Let's focus only on length contraction. And again, there's a lot of hogwash here, because what you find if you start talking about only focusing on length contraction, what this means here is it means this. That means assume delta t is 0 and delta t prime is 0. So look what happens. So if delta t is equal to 0, then I get delta x prime is equal then to gamma delta x, and then I'm going to get a term here that's 0. If I focus on the other case, delta t prime equal to 0, then look what I'm going to get. Delta x equals gamma delta x prime here, plus this 0 term here. So what you're really doing in this situation here is that 0 means what? That means that a measurement of time takes 0 time units. Now, if you're talking about everyday things here, you look at a meter stick, for example, and because you're not moving relative to the meter stick, you could see both ends of the meter stick simultaneously, right? So if I look at the analogy of measuring a meter stick, what I mean by this here is that you could imagine this is your meter stick, and we know this is 1 meter. Why is it that you could say that that's a 1 meter stick? Because when you look at it, your eyes see both ends simultaneously. Right? You can see them simultaneously. You cannot do that in special relativity. If you're going a substantial percentage of the speed of light, you cannot see the front and the back simultaneously. So what do textbooks do? They just say, hey, we're just going to assume that. That's hogwash. So we're literally giving you a white lie here. And so the way that we typically do that is that we just say, well, we're approximately doing it really, really, really fast so that we could then come in here and we go, we just assume that delta x, delta t is about 0 and delta t prime is about 0 because the length contraction part is bigger here. Okay, so that's the one thing that you gotta really be careful about. So what are the length contraction equations? Just like we did before, if I scan all the way back up and I look at these clocks, there's this, we have to compare these two types of things here. And so when I look at this guy here, then I'm going to do the exact same type of scenario here. I'm going to come in and I'm going to say, if I'm going from the S to the S prime frame, what do I mean by that? That means if I look at the equation, I'm going to get delta x prime equals to gamma delta x. Okay? And the way this is typically written is that this is going to be a little bit slippery because of the way it's written. So what the Lorentz transformation is really saying here is this, is that if I look at a meter stick, so here is one observer in this frame, and I typically call the S frame the one where you have this dude relative at rest to the Earth. But it's arbitrary. I got to pick one of them. It's arbitrary. So what I want to do now is that now I'm in a rocket frame that's moving. So as this rocket frame is moving here, this is typically what I call S prime. So S prime is always relative to Earth. So I'm always imagining that I'm this little red guy right here. And so of course the other observer is right here. Now each of these observers now have a meter stick. Right? So this is a meter stick. And then this observer has the exact same meter stick. So what I mean by this meter stick here is that it's only a meter in the proper frame of reference. So that means if I'm in the S frame, then this implies that the meter stick is at rest relative to red observer. Okay? And if I'm talking about the S prime frame, this is the meter stick is at rest relative to the green observer. So even though the green observer is moving relative to the red observer, in their proper frames, the meter sticks are different here. So what you find here is that if I continue to move along this way here, is that here's where the prime gets really funky here. And I'm gonna be really sorry to tell you this, but here it goes. So even though I boost from the S to the S prime frame, what we're really writing here, let me make sure I wrote this correctly. You know what I did? I hate to tell you this, I screwed up my primes. Let me make sure, I gotta come back up. Let me come back up here and I gotta look at these frames. Did I do that right? Oh, damn, I didn't put a prime in this guy right here. So this has to be a prime, that has to be a prime. I have a problem. I have a prime problem. And this is my problem right here. So if I'm in this frame right here, what you're going to see here is that if I'm in the S to S prime frame, it should read this here. It should be that delta X is equal to gamma delta X prime.
Why is that? Because that's like the opposite of how we've been doing it in the past.
Wait.
It seems like
No,
based
I
on
have a problem with the prime here. And the question is, oh, I know what I did wrong. I think I know what did I do this wrong? God, I can't see it actually. I'm not seeing what I'm seeing. So I have some mathematical hiccup here because this is what should happen right here. Okay? When I look at this, if I'm going to say that this is the proper length of the meter stick, and this is the relative length that is moving relative to the proper frame. What I should have is that I should have a gamma factor dividing that. And so my picture is showing me something not right here. And that's what I'm trying to understand. So I have a problem with my primes somewhere. So I'm gonna be a terrible person, and I'm gonna keep moving on. And I will find it and then come back. But ultimately, this is length contraction right here. This is the length contraction equation. And note, this is a very specialized equation. Why is it a very specialized equation? Because look at the time difference. That assumes that we could see both ends simultaneously, so that delta t and delta t prime is equal to 0. But if I had not kind of screwed up right now, what does this mean? This guy means here that this delta x, this means that this is the meter stick at rest relative to observer. This is the meter stick moving relative to observer. That's what I mean by moving. It's not okay to just say moving, but it's got to be moving relative to the observer. And since gamma is greater than 1, then I have shorter measurements by S looking at S prime. Okay, short. And if I was to kind of look at this thing a little bit, funny here, there's an image that I saw on the web that reminded me of particle accelerators. So this is sort of like what it looks like. So I have this image right here. So if you could throw a ball pretty fast, here's what you would see. If the baseball, let's say, was at rest relative to the observer, then this length right here would be the proper length. But if you throw the ball a significant speed, as you're seeing here and here, you're seeing that the baseball that typically would have let's say a proper length of, I don't know, 10 centimeters, just to be of the order of 10, you could see that these are shorter as observed from the proper frame. Now you may say, well, the baseball's kind of crazy, and then this picture is really crazy because they're saying that if you were to approach C, special relativity stops working, and what you find here is that things should approach, a width of a line, which means lines don't have width. They have length, but they don't have a width. So if you think that this might be kind of a little bit funny, this is actually proof of it in a particle accelerator. So the way a particle accelerator is, what they have is, so if you look at the Stanford Linear Accelerator, what they do here is that they have a beam that runs, the main portion of the accelerator is 2 miles long. What do I mean by 2 miles long? At rest relative to the Earth, SLAC's accelerator is 2 miles long. And what you have here right at the beginning is that you have a gun. There's an electron gun. And what the electron gun does here is it actually shoots pulses. So there's a pulse that it shoots and it goes down the beam pipe. So when the gun shoots a pulse here, it actually accelerates it pretty fast. It starts off at 9, 9. Dude, I'm getting old. I think it's this here. Yeah, 0.998. So the speed of the electrons at that gun, and by the way, the electrons reach that speed to, I don't know, a desk table length. It's very, very, very short. So what does the rest of the accelerator do? The 2 miles increases speed to 0.999998 C. That's what the 2 miles do. And what you can do here is that they look at the pulses. So you could imagine that this pulse makes it look like it's at V equal to 0, but this pulse is really at 0.998 C. So as you increase the speed right here is literally 0.999998 C. The beam literally length contracts. And you can actually see that with the detectors inside the accelerator. So if you didn't account for special relativity, you wouldn't see these beam pulses contract. I mean, you wouldn't know what was going on. So I think that's really interesting that you can see this contraction of the beam here. So what I'm really trying to show you here is that if I have an observer, the observer at rest will always measure the proper time, the longer distance. But as you, from the observer at rest to the one moving, they're always going to measure a shorter distance. So in essence, when I say rest, remember, that's at rest relative to what? The actual, their meter stick. When I look at this guy moving, that means they're moving relative to this. So this guy will always be longer, and this guy will always be shorter. Did I hear a question? Okay, so I have this time dilation. Damn, we're out of time. We got 2 minutes left. So note that I did this very simply. There's no thinking about this thing very much in terms of, besides my prime screw up, which I'll fix by the next time we meet. What we're going to be really looking at now is we now start the problem solving. And when I talk about the problem solving, there's going to be 2 pieces. There's going to be sort of like the conceptual plus drawing of space-time diagrams. And then there's going to be the mathematical piece. And what I want to say here is that I think that for the most part, I think we've gotten about as much as we can with the conceptual piece. Now, all we got to do here is that we have to sort of like put it together with problems and drawing of time versus position graphs to actually nail this stuff down.